Hello all, welcome to the video lecture on signals and systems. We are discussing about Fourier transform, and this video would be on problems on Fourier transform. We will discuss a few basic problems on how to apply Fourier transform for a few particular signals. Moving on, the first question is find the Fourier transform and sketch the magnitude and phase spectrum of the signal x of t equal to e power minus at u of t. So this question, if you remember, this is a one-sided exponential signal, and we have already discussed this problem in the previous video. But still I have kept this problem here so that I could give you a broad explanation of how the magnitude spectrum and the phase spectrum can be calculated. However I teach you to calculate the magnitude spectrum and phase spectrum, you can apply the same method to whatsoever problem it is. So in the previous video, I've told you orally like how it has to be done. Here I'm going to explain you manually on how this has to be done. So moving on, by the definition of Fourier transform, we apply x of j omega equal to integral minus infinity to plus infinity x of t e power minus j omega t dt. So our x of t here is e power minus at. So substitute that here, integral minus infinity to plus infinity e power minus at e power minus j omega t u of t. So what is u of t? By definition, it has a value 1 for values of t greater than or equal to 0. It has a value 0 for values of t less than 0. So what we do here is we substitute the value of u of t as 1 and we make the limit as 0 to infinity. So as you can see, x of j omega now is equal to integral 0 to infinity. We have two e power terms, so combine both the terms, e power minus of a plus j omega t dt. So when you take integral of e power theta, it's the same e power theta divided by the variable value. So we have it as minus 1 by a plus j omega into e power minus of a plus j omega t 0 to infinity. So the concept is upper limit minus the lower limit. Wherever you have t, you will have to apply. So here minus 1 by a plus j omega e power t is here. So then you substitute minus infinity, you get it as minus infinity and you get it as e power 0. So e power minus infinity minus e power 0. So e power minus infinity is always 0. E power 0 is 1. So substituting it, minus 1 by a plus j omega, 0 minus 1. So you get the answer as 1 by a plus j omega. So this is the Fourier transform of the signal e power minus at u of t. Now moving ahead, we will see how to calculate the magnitude spectrum and the phase spectrum. Now to calculate the magnitude spectrum, follow this method. X of j omega. Now we are going to we will actually resolve this 1 by a plus j omega such that we can be able to split into real and the imaginary part. So what we do is multiply and divide by the complex conjugate. So 1 by a plus j omega multiplied by a minus j omega by a minus j omega. So wherein your numerator now would be a minus j omega divided by denominator goes as a plus j omega, a minus j omega. So this is a plus b, a minus b, which is nothing but a square minus b square. So you get it as a square plus omega square. So now what we will do is, your numerator is a minus j omega. This is clearly in summation. So then we will split it as a by a square plus omega square minus j omega by a square plus omega square. So now we have had our Fourier transform as real part plus the imaginary part. So by formula, your magnitude spectrum is square root of real part square plus the imaginary part square. Phase spectrum is tan inverse of imaginary part divided by real part. So now to calculate the magnitude spectrum, what we will do is, as you can see, you have values of a here and you have values of omega here. So you have to substitute different values of frequency to get the magnitude spectrum ranges. We'll have to calculate at least a minimum of 10 values so that we could get a range to draw the graph. And what about a? A value, what we will do is, we will keep it constant as 0.5 or 1. Here I have shown you both the cases. First we will discuss with a equal to 0.5 and then we will discuss with a equal to 1.0 and we will plot the graph for both the cases. So this is how you will have to do the magnitude spectrum and the phase spectrum. That is, in general we call it as a frequency spectrum graph. So as you can see, I have my omega values here. The j omega values are calculated by this way. The magnitude is calculated here and the phase is calculated here. So what are we actually doing? A value is kept constant as 0.5 throughout, but the omega value we are having it through a variable range. We start from -8 till 6. You can go up to how many ever values you would like to, but at least try to calculate a minimum of 10 values so that you could plot a range of values. So as you can see, I have calculated all the magnitude values here and the phase values are being calculated here. So these magnitude values and these phase values are plotted in a graph so that we would be able to view the spectrum. So this tabular column goes for a equal to 1. Similarly, the x of j omega, I mean the magnitude and the phase spectrum are calculated for a wide range of omega. So finally, the magnitude spectrum and the phase spectrum graph goes like this. Now the one you can see is a magnitude spectrum graph. When you plot the various values you have got, your graph will somewhere look like this. So this graph, this shorter wave is for a equal to 1. And this elongated wave, you get it for a equal to 0.5. And this goes as your phase plot. So this is how you will have to calculate the magnitude spectrum and the phase spectrum for any given signal.